So far we've looked at one particular type of locus, which is where we've got the modulus of z minus some complex number is equal to r. And we know that that's a circle, centre z0 with radius r. We're going to look at a second type of locus, which is where you've got one modulus equal to another modulus. So we're going to look at two different ways of thinking about this. Let's think about it geometrically first. So the first thing that we're going to do if we think about this locus geometrically is we're going to write each modulus is going to have z minus something inside it. So we've already got z minus 3 here. Obviously you don't need to put the 3 in a bracket. And then on the second modulus, I'm going to write that as z minus, and then inside the bracket we're going to have to put minus I to make sure that when we multiply out that bracket we get the original equation, which is plus I inside the modulus. So remember what this means geometrically. We've got one complex number take away another complex number. So this is the distance between z and 3. And remember, 3 is just like a coordinate, it's a point on the Argand diagram. And that's equal to, well, this thing here is the distance between z and minus I, because we've got z take away minus I. So we're looking for all the points z where the distance between z and 3 is the same as the distance between z and minus I. So let's sketch 3 and minus I. So 3 is going to be, say, here, and minus I is going to be down here. So we've got these 2 points, and you might remember that all the points that are the same distance away from this point and this point is the perpendicular bisector of the line segment between the 2 points. So we draw a line segment between the 2 points, and all the points that are the same distance away from this point and this point, which is what we want, is on the perpendicular bisector of that dotted line. So that's 90 degrees there. So let's just check that our understanding of this is correct. So if we pick any point on this line, what we're saying is the distance between z and 3, so that distance there, is going to be the same as the distance from z and minus I, which it will be because that's 90 degrees. So you've got two similar triangles. So in general, if we've got a locus that says z minus z1, the modulus of that equals the modulus of z minus z2, that's going to be the line that's the perpendicular bisector of the line segment that goes between z1 and z2. It's also really important that you understand how to derive this algebraically. So let's have a look at how to do it algebraically. So when we derive it algebraically, we always start with z is going to have the coordinate xy. So z as a complex number is x plus iy. And we're looking for all the pairs xy that satisfy this condition. So let's sub in x plus iy for z. And then we're always going to do the same thing, no matter what the locus is. We collect together the real parts and the imaginary parts. So we've got x minus 3 is the real part, and y is the imaginary part. And then inside this modulus, we've just got x is the real part, and then we'll take I outside of a bracket, and we've got y plus 1 as the imaginary part. So remember what it means to take the modulus of a complex number. We've got this is a complex number in green here, and when we work out the modulus of a complex number, that's the same as doing the square root of the real part squared. The real part is x minus 3 plus the imaginary part squared. The imaginary part is y squared. And remember, you can think about that as you've got some complex number, this green complex number. The real part is x minus 3, and the imaginary part is y. So your complex number is there somewhere. Then you can draw a right angle triangle, and the modulus is the length of that hypotenuse. So we've basically just done Pythagoras on this, this point here to work out that length. And then let's do the same for the modulus of the complex number on the right hand side, the square root of the real part squared plus the imaginary part squared. Okay, well, we can square both sides of this equation. So we'll get x minus 3 squared plus y squared equals x squared plus y plus 1 squared. And then we'll just have to multiply out the brackets to try and simplify it. And you should always find that your x squareds and your y squareds cancel each other out, because obviously we want the equation of a line. So we get the equation of the line, which is y equals minus 3x plus 4. Now obviously another way of working out the Cartesian equation of the line would have been to actually work out what is the equation of this perpendicular bisector. In part B of the question, we want to find out what's the minimum possible value for the modulus of z. So we know that z has to lie on this line with the equation that we found before. Well, we basically want to find out where does z need to be to make the distance between the origin and z as small as possible, because that's what the modulus of z means. Well, as we move z along the line, you might be able to see that the smallest distance between the origin and z is going to occur when the line from the origin to z is perpendicular to the locus of points where z can be on. So we've basically got to solve this problem and find out what is the length of that dotted line. So I guess there's a few ways to do this. We know the equation of the locus is minus 3x plus 4. Therefore, we know that the equation of the line that's perpendicular to that going through the origin, well, it's going to have gradient a third, so y equals a third x, and the y-intercept is 0, so y equals a third x. So I guess we could find out what the coordinate of z is, and then work out how far away is that from the origin. So let's find out what the coordinate of the point of intersection of these two lines is, and that will give us the coordinate of z that's closest to the origin. So we're going to solve a third x equals minus 3x plus 4. So x equals minus 9x plus 12. So x equals 12 over 10 or 6 over 5. Then we can find the y coordinate. So y equals a third x, which is a third of 6 over 5. So we know this coordinate is 6 over 5 and 2 over 5. So all we need to do is work out what's the length of this dotted line here. That's what we're trying to find, because that's the minimum value for the modulus of z. So we can just use Pythagoras to work out what the modulus of z is. Another way of thinking about this is a complex number, which has real part 6 over 5 and imaginary part 2 over 5i. So we're just working out the modulus of that complex number. So modulus of z, when it's at a minimum, is going to be the square root of the x coordinate squared, or the real part squared, plus the imaginary part squared. We're basically drawing a right angle triangle like that. And we'll get 2 root 10 over 5.